Добрый день, здравствуйте. Сегодня мы обсудим, что такое image processing в общем и что можно, какую выгоду можно иметь с image processing, кроме как развлечения. Так как терминология в основном на английском, на русском будет только предисловие и заключение. Все остальное я буду говорить на английском языке, так как эта терминология мне больше знакома. Okay, so first of all, we'll give a short overview of what is in image and image 3D in general in Mathematica, to understand the basics of importing and manipulating the image as an object, as a Mathematica object. Then we'll go into details a bit more about what information we can get out of it, or how can we use that information in order to create new images or update the existing one. And then we'll go over, we don't have that much time to go into details into everything, so we'll just cover the main topics like pixel operations, morphology, segmentation, filtering, and I will provide you with some fun examples, and we'll try to keep everything as much interactive as it is possible, actually. So going into the image and image 3D representation in Mathematica. In general, there are two different types of images, global types, image and image 3D. We'll go starting from image, and then we'll continue with image 3D. Importing in Mathematica an image is way much easier than anyone can imagine. There are like multiple ways to doing that, from copying and pasting in and drag and dropping and importing, like the previous colleagues showed it earlier. So when having some image like this, you can import, you can typically resize it. You can, if you left click on it, you will see, you can move it, you can see the size dynamically changing on it, and basically you have all operations when you click, when you are doing right click on it. The data types of image that are supported in Mathematica are 5 of them. So bits, bytes, bit 16, real 32, and real. In general, this is quite enough to support most of possibilities. The color spaces is the, let's say, one of the basics of when working with actually images. Typically, we can get the color space of the image using 2 different ways. The first way is getting out of options, since the color space is an option of an image. But in that case, we'll have a list of rules. This is an alternative to association, like previously was already explained today. And we can just have use image color space common to get the color space by itself. So this is a 3-channel RGB. Since the image has channels, and this particular image also has 3 channels in here, we can separate it into 3 different channels. So having 3 R image, G image, and B image. So this combination gives us this nice picture. There are 3-channel, 4-channel images, which include RGB, HSP, XYZ, and etc. And there is CMYK, which is the 4-channel, but we can also create multi-channel images. We can create 9, 16, 32, 64, like whatever, how much channels we want, we can create, and Mathematica allows that. Basically, if image channels will give just the number of the images, because the number of channels, sorry, if we don't want to go into details and see what channels they are, but just to know the number of channels. A very interesting and important, actually, option property of the image is the interleaving. These 2 matrices, 2 representations show what is the main difference when the image, we say, is interleaved or it is not. So in the planar representation, we can see that the channels are grouped by 1. So we have here R matrix, G matrix, and B matrix. And in the interleaved, we can see it's like RGB, RGB, RGB. And this is something that is widely used in Mathematica, and this option is available not only for images, but for 3D images, for graphics, and etc. Last but not least option that I want to talk about is an alpha channel or the transparency channel. Besides getting the alpha channel, we can set and remove the alpha channel of an image. So having this cute lady here and setting an alpha channel, we will have this representation. And we typically can remove all alpha channels from this image and get the original one back, or we can just remove select a particular color that we want to work with, white or black. So in this case, if we take the image with alpha channel and remove the white and black, we can see that when we remove the white one, nothing changes actually, because there is nothing to remove. But when we remove the black, we can see this channel set in here is now black colored. For 3D images, mainly pretty all options and properties are the same as for 2D images. The main difference that we have in 3D images is the coordinate system, and it's for 3D images we don't work only with 2 dimensions, which is width and height, but we need to consider also the depth. And this image illustrates, you can see here, I'll just, okay. This illustrates the way that the coordinate system for 3D images is constructed actually. We can see that X goes from 0 to the maximal width, and Z goes from 0 to maximal height, and Y goes to maximal depth. And the coordinate systems, there are like multiple coordinate systems in Mathematica. But this one is the most basic one, which illustrates and gives clear understanding how they are actually constructed. This is a famous example of bug, Mathematica bug. What we did in here, we took the 3D object and we can blend the colors in color function, and we can colorize our bug with parts of segmentations that we will talk a bit later on, and we will have this kind of result, and we can clearly manipulate it by rotating, resizing, and moving the bug. So this is fully supported and automated 3D model in Mathematica. We also can create nice animations that illustrate some manipulations with 3D objects. Like in this case, we have a 3D cellular automation manipulation. There are like multiple examples working with 3D images and objects, but not to go into details with everything, we can take an engine block example and try to find out like all the edges in 3-dimensional system, and we will see that it's working. Yeah, and okay, so here we can see that all the edges of our image, and this is again a 3D object that we can manipulate the way we want to. When left-clicking on an image, we have a tooltip that allows us to go and to do basic manipulations without going into details in the syntax. We don't need to know any functions or whatever. In this particular case, this is the tooltip for the Mathematica bag, and we can see here the image in different offsets and in different states. How the histogram changes when we change actually the color space, or we grayscale the object, or whatever we do, we can dynamically follow up with it. As I already told, the coordinate system of 2D and 3D images are kind of different, but the idea is very important, and let's say the most primitive and maybe the most important thing is to get the dimensions of our image. So taking again the picture of lady, we can see that this is 120 on 120 image, and we can see the aspect ratio is 1, and this is These all are the basics that are supported, and these are the main things that everything is constructed on. A very interesting thing is an image data function, which actually allows to work with image not in digital way. So getting and extracting values, selecting regions, and in combination with an image take function, we can construct, we can crop the images or do other manipulations which require any kind of regions or region filtering. Taking this example of Fox here, we can see what it looks like. We can just show less or show more. These toolbars are supported on everything and are really reliable helpers in everything. Clicking on show all, we'll see the whole image data, but we don't want to do that now. And we can represent a part of it, like from exact coordinates in the matrix form to have a better understanding what is going on here. If we plot them, we will have a better understanding here. What it does actually. We took this image and we actually take the pixel values that are gray, absolute gray, and plot them here. What it can be used for, this manipulation will show up. In this example, we take the black pixels and put a variation on manipulation so that we can see how the pixel values vary in this image. So this is a grayscale image, so we work only with black and gray pixels to have a better visual perception of it. So we can see how the image is actually constructed from black and white pixels. Image levels is again a very important thing. These are the main data extraction functions: image data, image take, image levels. The most important image data extraction functions that are used for absolutely multiple fields and things to understand or to calculate. If we want to reproduce the image data, let's say on a 404 matrices with a planar representation, we will see that this is the planar representation of 404 from 94 to 100 and 90 to 93 coordinate region for the grayscale image that we had before. The other options and properties are again easy extractable. We have an image measurement function that will extract the mean intensity, and multiple other things that we may be interested in the image in general, absolutely. Also the histograms, we can't miss it, and this is a representation that is also accessible from the toolbar and can give a clear understanding of an image and how it actually is represented. I want to speak a bit about pixel operations, which include everything that relates actually to color, like grayscaling, highlighting, adjusting the levels. These all are used to be in the pixel operations section. And in this example, oh, sorry, I forgot to initialize the image. We can see the differentiation, like we have this image that we had here before also, and we can see the pixel operations that are done. I'm pretty sure all of you are familiar with this and are done this with your mobile phones or whatever, and this is the mathematical representation of the image and how it is done. But we don't, if there is something that doesn't really cover our needs, we can create our manual pixel operation and take, for example, partly uncoloring and extracting some colors from the image that we are not interested in. In this image, we can see that the windows are blue in here, and we just extract it and grayscale the images, but we didn't touch the flower by itself. As for histograms, one interactive and interesting example, we can see the histogram of the image, as we already told about it, but what we can also do, we can combine and transform the two histograms from two absolutely different images. So in this case, we have here maybe May in Great Britain and late November, and when combining these two, we will have something early autumn, and this is a nice representation how the histograms can use to be transformed from one image to another and combine a new one. A bit about geometric transformations. Whatever we do with the images actually is a geometric transformation in sense if we move them, if we rotate them, if we apply any transpose or transformation matrices on the image is called geometric transformation. And there are typically two types of geometric transformations. And the image rotation, for example, is the most basic example that we can see on most basic example of geometric transformation. The two types that I'm talking about are forward and backward transformations. The main difference is in forward, in one case we have the original image and we move to the new coordinates, we transpose to the new coordinates that we need, and in the backward we do inverse transpose to get the image. And what are the results differences is actually easy visible in here. So we have like typically not that, but a bit different results in images. So that's about technique. But if we go into a bit more complex examples, here is an example of a spline grid. And this is a dynamic spline grid, and this we can move the points, and we can see how it dynamically transforms. And this is more complex example, a real example that can be used, for example, in 3D gaming or some other related field. Going back to our presentation, as I said in the example of Mathematica back, I mentioned filtering. Filtering is maybe not most, but one of most important thing and mathematical influences that can be applied on the image, and it's actually quite heavy operation. So for maximal performance, all possible parallelizations are done, and for that cases, for example, MKL and IPP, which are like Intel libraries, are used to accelerate the performance and obtain a good performance. And we can apply absolutely different filters on the images and get different results. I'm pretty sure again the results in here will be very familiar to you. Yeah, these are just only few of them and few variations. Again, basic examples just to have an understanding what means to filter the image and what results can be achieved using the filtering. This type of filtering is called local filtering, but there is a non-local filtering also. What is non-local filtering? For example, one of best examples of non-filtering is an in-pane. As we can see here, in this example, we have an image which is corrupted actually, and we have the, let's say, bordering of the corruption, and we can easily fix the image and have a normal one. And this is, I think, a great result. We can repair parts and the whole images. Another dynamic example we can see here just an image, and this is a quick dynamic manipulation of the non-local filtering. So we have here masks of the animals, background, foreground, and the ground, and we can just blur or erase. This is an effect of blurring or erasing the mask, and we can see that we blur it. So we can do that on the animal for better perception, and we can see what is the result of it. So this is all done in Mathematica. I'll just, yeah, I can't resize it. Okay, yeah. Another example of non-local filtering is a deconvolution, which deconvolves the image with according with respect to a predefined kernel. So let's say we take this example as a basic image, and we define the Gaussian matrix kernel for us, and we convolve the image. So now we have a blurred, low quality image. And now we perform two types of deconvolution. We can see the actual difference of the images, the quality when we define or when we do not define the grayscale precision. In this first example, we have maximal result, and in the second one, it's a bit more blurred, but it's again quite nice result. And we can easily also remove the noises. I don't know if you see this, but this image has quite big noise. This type of noise is called poison noise, but there are like multiple other types of noises. So if we know that there is a poison noise, we can easily remove it from the image, so having a picture without noise. Going quickly over morphology, we can see again in the comparison results what we can do with that. The examples of morphology performance results are erosion or dilation, and this can be used for thinning, pruning, skeletizing examples and stuff like that. So these are some of the examples that I told, and we can actually go on because there is something that I want to show, but I don't have that much time. One very interesting thing is segmentation, which has a goal of differentiating the foreground and background and working the images. And the result that can be achieved using the segmentation is, for example, colorizing the grayscaled images in the exact regions, or having X-ray images and growing the region by the given point that we have to, and having colorized it. This can be widely really used in the medicine, or the water sheeting. So having segmenting the image of heart chamber, we can really find the maximum extremum points of the image and colorize them, so having clear understanding what is the problem in here, or if there is no. There are multiple other examples of segmentation inside, so you can just look in later, but the one I want to show, which is a quite interactive one, is the solving maze. So we have maze in here, and we can solve it automatically, so finding out the region that is acceptable as a solution and colorizing it. We will finalize in an image where the white shows the correct solution in this, and this is also acceptable for multiple solutions. So if we have multiple solutions, we will have again it colorized on this image, and we can see that. A bit about registration. There is two types of registration: dense registration and sparse registration. So in a sense of dense registration, a nice example that illustrates the whole meaning of it is an example of MRI and PET. so that we can use Mathematica to get out the normalized mutual information, and plotting it, we can see the lower extremum point in here, and taking that, we can actually use that to construct a new image and finalize it in something like this to see the actually. What is done here, we take two images and combine them into one. There is something else that I want to show, but I'm out of time, so you can just watch my presentation, and there is a nice example of collages and word clouds in here. So, but there is no time. Thank you.